Buenos días. Finalmente llegó el momento, llegó el día, así que estamos todos acá preparados para darle la bienvenida y para escucharlo al Dr. Walter Boron. No necesita, supongo, demasiada presentación para ustedes. La mayoría de ustedes lo conocen muy bien, o por lo menos conocen muy bien cómo escribe. Pero les cuento que el Dr. Walter Boron es profesor de Fisiología y de Física Biológica en Case Western Research University en Ohio. Y además es el jefe del departamento de Fisiología y Física Biológica y también de Bioquímica. Y tiene una amplia experiencia tanto en lo que es educación o educación médica, enseñando en medicina, como haciendo investigación básica. Así que, bueno, hoy tenemos el honor de recibirlo. Antes de la conferencia nos acompañan en el estrado el decano de la Facultad de Ciencias Médicas, el profesor Dr. Juan Basualdo, el secretario académico de la facultad, el doctor profesor Mario San Mauro, y en este momento va a decir unas palabras el decano de la facultad, recibiéndolo al doctor Boron. Así que los dejo con el decano.
Bueno, buenos días a todos, buenos días, profesor. Como todos ustedes están más interesados en escucharlo a él que lo que uno pueda llegar a decirles, voy a proceder a leerles las resoluciones de la facultad y las resoluciones de la universidad con respecto a la visita del profesor Walter Boron. En el caso de la Facultad de Medicina, visto las presentes actuaciones, atenta a la realización en esta Casa de Altos Estudios de una conferencia abierta a toda la comunidad educativa sobre la homeostasis del equilibrio ácido-base a realizarse el día 12 de noviembre, considerando que el doctor Walter Boron es un distinguido profesor de Fisiología y Biofísica de la Facultad de Medicina de Case Western Research University, Cleveland, Ohio, y es autor de uno de los libros de Fisiología Médica de referencia de la Cátedra de Fisiología y Física Biológica, a la autorización conferida al decano por el Honorable Consejo Académico en sesión de fecha 26/8 del 94 para el tratamiento de designaciones de huésped de honor. Por todo ello, el decano de la Facultad de Ciencias Médicas resuelve, artículo primero, declarar huésped de honor de esta Casa de Estudios al profesor Dr. Walter Boron. Artículo segundo, regístrese, comuníquese con nota de estilo al profesor Dr. Walter Boron. Firmado por quien les hago. Por otra parte, la Universidad Nacional de La Plata presenta la siguiente designación, visto estas actuaciones, por las cuales la Facultad de Ciencias Médicas informa sobre la visita que realizará a esa facultad del profesor Dr. Walter Boron, con motivo de brindar una conferencia abierta a toda la comunidad educativa sobre la homeostasis del equilibrio ácido-base, el día 12 de noviembre próximo, y considerando que este ilustre visitante es doctor de Fisiología y Biofísica, distinguidísimo profesor y jefe del Departamento de Fisiología y Biofísica de la Facultad de Medicina de Case Western Research University, Cleveland, Ohio, que entre otras distinciones recibió el título honorífico Summa Cum Laude en 1971 en St. Louis University Chemistry, que además es autor de uno de los libros de Fisiología Médica de referencia en la Cátedra de Fisiología y Física de la Facultad de Ciencias Médicas, que la Universidad Nacional de La Plata se siente complacida y honrada con la presencia en nuestra ciudad de tan relevante personalidad. Por ello, y atento al establecido en el artículo 2 de la resolución número 1761/78, el presidente de la universidad resuelve. Artículo primero, declarar huésped de honor extraordinario de la Universidad Nacional de La Plata, mientras dure su permanencia en nuestra ciudad, al profesor Dr. Walter Boron, con motivo de la visita que realizará a esta Casa de Estudios, con el fin de brindar una conferencia abierta a toda la comunidad educativa sobre la homeostasis del equilibrio ácido-base el día 12 de noviembre próximo en la Facultad de Ciencias Médicas. Artículo 2, disponer el otorgamiento del diploma que acredite la distinción acordada por la presente al profesor Dr. Walter Boron. Artículo tercero, de forma.
Bueno, les agradecemos entonces la presencia a las autoridades de la Facultad de Ciencias Médicas, al doctor profesor Juan Basualdo y doctor profesor Mario San Mauro, y vamos a dar comienzo entonces a la conferencia del profesor Walter Boron. Muchas gracias. Your turn. Yes. Everything is yours.
Where did he go?
Just no, I'm going downstairs.
Okay.
And that's your home.
Okay. Well, thank you very much for an outstanding welcome and introduction. It's my distinct pleasure to be with you this afternoon to deliver this lecture on one of my favorite topics, which is to say acid-base homeostasis. And this lecture is devoted to presenting my understanding of how the whole body is regulating its acid-base balance. So without further ado, I'd like to send you my welcomes from the city of Cleveland. And this is home to the Cleveland Orchestra, which is one of the finest orchestras in the United States. And Severance Hall, which is what you're looking at here, is just about a 5-minute walk from my laboratory. I also like to bring greetings from the Cleveland Museum of Art, which is also one of the finest art museums in the United States. And going from the sublime to the ridiculous, the Rock and Roll Hall of Fame, which is also located in downtown Cleveland. I previously was the Secretary General of the IUPS, and on behalf of the IUPS, I'd like to wish you all, send you all an invitation for the 39th Congress of the International Union of Physiological Sciences, which will be held about 3 years from now in China. So I hope to see many of you in Beijing. So this is an outline of what I'll be discussing this afternoon, and by way of introduction, I'd like to ask why, where, and what about acid-base balance. And so the why is, why should we care about acid-base regulation at all? And the answer is that virtually every biological structure and process you could imagine is sensitive to changes in pH. Some of the observations, namely changes in pH, affect just about everything, physiological chemistry inside and outside of cells, receptors, channels, transporters, structural proteins, the list goes on and on. Moreover, changes in extracellular pH on the outside of the cell we'll see affect the intracellular pH of cells, and this is the reason why changes in extracellular pH affect just about everything, because these things that we were just talking about, some of them are on the outside of cells, but most of them are on the insides of cells. So understanding whole body acid-base homeostasis, which is to say the control of extracellular pH, is intrinsically important. Many pathological conditions are associated with defective acid-base homeostasis, and here I'm listing just a few of these so you get some sense of what we're talking about. Widespread deficits, which could involve protein missorting or vesicle fusion via the porosome, but also various maladies in the central nervous system. And to this list, I could also add, under the aegis of NBCE1, suicidal ideation is believed to be associated with NBCE1. Various kidney disorders, the cornea, the stomach, and various other parts of the body are all associated, either in normal physiology or diseases, are associated with changes in the acid-base status. So the where is where you can learn more about this, and this is a shameless advertisement for my textbook. And so if you really want to learn more about acid-base physiology, you should look at the textbook. And one general principle is, although the body has many acid-base buffers, like phosphates and so on, acid-base homeostasis is really the story of regulating CO2 and bicarbonate, particularly in regulating the ratio of CO2 to bicarbonate, because it is this ratio that determines the pH. And so where you might find these things in the textbook, in chapter 28, you'll learn about physiological acid-base chemistry. In chapter 31, you'll learn about how ventilation, the lungs, the ventilation of the alveolar air spaces, control the CO2 concentration in the blood. In chapter 32, you can learn about the feedback loop, about how changes in oxygen, CO2, and pH affect ventilation and vice versa. And then finally, in chapter 39, you can read about how the kidney controls the bicarbonate concentration in the blood. And so during this lecture, I'm going to be referring to figures that are in the textbook, and I'm going to give you a merged view of the textbook story of how to understand pH regulation. And the what is the CO2 bicarbonate ratio, and it's linked to respiration. So when thinking about whole body acid-base status, it's intimately linked to whole body respiration, which is to say both the oxygen uptake and the CO2 production. And the reason, of course, is that the most important buffer pair in the body is the CO2 bicarbonate buffer system. And so to reintroduce you to a figure that you probably recognize from the textbook, at least at this stage of the game, but I'm going to make it far more complicated, is that when we inhale, we bring oxygen-rich air into our alveoli. So in this diagram, this is meant to represent all of the alveoli of our lung, and this is meant to represent the conducting airways. This oxygen that then moves across the alveolar blood gas barrier combines with hemoglobin to form oxyhemoglobin, and it's in these red blood cells that the oxygen is transported to the systemic tissues, and eventually that oxygen finds its way to mitochondria to support oxidative metabolism. At the same time, the mitochondrion produces CO2, and that CO2 moves in the opposite direction, and to some extent will combine with water to form bicarbonate ions and hydrogen ions. In addition, various metabolic reactions that occur inside the cell will also generate hydrogen ions and affect this equilibrium. So one can imagine the general format for a buffer, and so you can imagine that when hydrogen ions are produced, they can react with a weak base with a valence of N, and then when the hydrogen and that weak base bind together, they form the same buffer base, but now with a valence of one positive charge more. So in the case of the buffer being ammonia, you end up with ammonium, which is a single positive charge. In the case of phosphate of the form HPO4 double minus, so there's two minus signs there, you now form H2PO4 single minus. And in the case of bicarbonate, you form carbonic acid. So in each case, the B has added one proton that can become a molecule with a positive charge, a negative charge, or no charge at all. And in the case of carbonic acid, one of the things that makes it so special is that the carbonic acid itself will dissociate to form hydrogen, CO2 molecules in water, although this reaction is very slow. And so all of these can be described as we see up here on the upper left corner, that the dissociation constant is equal to the product of the base times the hydrogen ion divided by the concentration of the protonated species. So if we take that equation and begin to put it into a logarithmic form, I won't bother deriving the equation, but this equation directly yields the familiar Henderson-Hassebach equation, which tells us that the pH of the solution is equal to the pK, which comes from there, plus the logarithm of the bicarbonate to CO2 ratio. So it's the ratio of bicarbonate to CO2 that's important for determining pH. So how do we regulate this whole process of respiratory exchange? And it begins up here in the brainstem, where there are several controlling areas, both in the medulla and the pons, although mainly in the medulla. And from the medulla comes motor output via an intermediary neuron that will be innervating muscles of respiration. Because unlike the heart, which has an intrinsic rhythm, the lungs have no rhythm at all. The rhythm is imparted by the brain, which controls skeletal muscles. Also, there are a series of sensors for oxygen, CO2, and pH that sense the concentrations of each of these so-called blood gas parameters in the arterial blood and send messages back to the brain. So speaking of the brain, this is meant to represent a small vessel in the CNS, and these structures around the vessels are astrocytic emphyse, which surround almost every piece of vasculature within the central nervous system, including these vessels. And on the other side of this blood-brain barrier are neurons, and these neurons are consuming oxygen and producing CO2. Some small subset of neurons are central chemoreceptor neurons, and these, when the pH of the blood goes up, lead to a fall in the pH in the brain extracellular fluid and cause these central chemoreceptor neurons to change their firing rate. In addition, so now we've just talked about how the CO2 can be sensed. How is the bicarbonate sensed? So the bicarbonate is also sensed by these same sensors because that can affect ventilation, but CO2 and bicarbonate also are sensed by the kidney. There's doubtlessly some pH sensors in the distal part of the nephron, but most of the pH sensing is done by a set of actually a molecule with dual binding sites that senses CO2 and bicarbonate, and this is discovered by my laboratory. We're only going to allude to that in this lecture. The upshot is that when hydrogen secretion into the urine goes up, this increase in hydrogen secretion leads to an increase in the bicarbonate concentration of the blood. And so now we've talked about how the bicarbonate can be sensed. So now I'd like to tell you a little bit about the rest of the scheme. And so it turns out that, of course, all cells have a pH. We refer to that as pHi for intracellular pH, and the intracellular pH is regulated by a few families of ion transport systems, and here is my favorite, the sodium bicarbonate cotransporter, the electrogenic NBCE1, that tends to make the pH of the cell alkaline. And so this transporter, as well as others, is responsible for regulating the pH of the cell. And so one of the things that the Boron lab does is to study pH regulation in such cells, and we'll see later on that changes in the pH of the blood by affecting transporters like these can also change the pH of the cell in the same direction. One other story is that these red blood cells that I was showing you are not simply sacs of hemoglobin. In their membrane, they have very special proteins, and one of these proteins is aquaporin-1, which I'm representing by this channel here, but all of these little channels around the red blood cell membrane. And these channels are not only permeable to CO2, but they're permeable to CO2 and oxygen. So here, when the CO2 is produced, that CO2 passes into the red blood cell through aquaporin-1, as well as the RH complex in red blood cells. Both of these are wonderful CO2 channels. And when the red blood cell takes up oxygen in the lung, it does so by moving the oxygen through both the RH complex and the aquaporin channels. And here in the systemic tissues, when the oxygen is released, the oxygen goes through these channels. So almost all of the CO2 and oxygen movements in a red blood cell are through channels. And one of the other things my lab studies is the movement of gases through these channels. And it was our laboratory that first described gas channels. And so these gas channels exist on many endothelia in the capillaries of the systemic vasculature, including both the systemic and the pulmonary capillaries. In the case of the alveolar type 1 pneumocytes that line the alveoli, they're the richest source of aquaporin 5. And at the blood-brain barrier, at the astrocytic end feet, is the richest supply of aquaporin 4. In fact, the aquaporin 4 is so abundant at the end feet of the of these astrocytic membranes that these aquaporins make up 35% of the entire membrane surface area. So one thing we'll talk about today is the kidney and its ability to control acid-base metabolism, and the other thing we'll talk about is the central nervous system. So now that we've completed the introduction, we'll now have a brief consideration of the chemistry of buffers in a closed system. So we already talked about the general weak acid HB with a valence of N+1. We call that a weak acid, and its conjugate weak base is the same chemical species, but without the hydrogen ion bound because it's now been separated, and this is known as the conjugate weak base, if that's the weak acid. In addition, if you could also think of this as a weak base, in that case, this is the conjugate weak acid. So we have weak acids and weak bases that are part of a buffer pair, and this is the general description. So we've already talked about some examples of different kinds of chemicals that can be either a weak acid or the conjugate weak base, all of which are described by this equation and the Henderson-Hasselbalch equation, which is specific for CO2 and bicarbonate. So what happens if you add hydrogen ions to the solution in the form, let's say, of hydrochloric acid, or what happens if you add hydroxyl ions to the solution in the form of sodium hydroxide? This is an example of metabolic acidosis, which we abbreviate MAC. This is an example of metabolic alkalosis, which we abbreviate MELC. And we're going to talk today about how the body responds to each of these maladies. So a comment would be that understanding a system with multiple buffers can be extremely complicated because there's so much chemistry going on simultaneously. And the Davenport diagram is a tool, a graphical tool, designed for understanding these kinds of interactions. So the Davenport diagram, which will be the next thing that we talk about, has two major components. It has one set of components that are designed to treat all non-bicarbonate buffers that are grouped together as if they were just one gigantic buffer. And it has some other considerations, as we'll see, that talk about the CO2 bicarbonate buffer pair. And note that both 1 and 2, both the non-bicarbonate buffers as well as the bicarbonate buffers, are competing for the same chemical, namely for protons. So they're engaged in a never-ending battle. So how do we understand multiple buffers? And I'm going to present you this, I just switched batteries, and I seem to have managed to bring with me a spare set of batteries that, unless I put them in upside down, which is possible, that my spare batteries don't work either. We'll see in a second. So I'm presenting to you the completed Davenport diagram, and what we're going to do in the next few slides is we're going to go through how one creates, backwards batteries. Quandoque dormitat bonus Homerus, which is a Latin phrase that means sometimes even the good Homer falls asleep, and this time it was the good Boron who fell asleep. Okay, so this is the Davenport diagram, and one key element is this line, which represents all non-bicarbonate buffers. And another key element are each of these three curves that you see here. And each of these curves describes the buffering capability of the CO2 bicarbonate buffer pair. And what I'm going to do with you today is show you how we ended up with this Davenport diagram in the first place. But just to continue the orientation, in this case, the blue curve describes what happens when the PCO2 is 40 millimeters of mercury. When the PCO2 is 80 millimeters of mercury, another curve here in green, it's exactly twice as tall because there's exactly twice as much CO2. And here, the third curve is half as tall as the blue one because it refers to a concentration of a PCO2 of 20 millimeters of mercury. So we're plotting the bicarbonate versus the pH, and each of these three curves, blue, green, and copper tone, each of them refer to the CO2 bicarbonate equilibrium, but at different CO2 concentrations. So let's think about buffers in a closed system. So a closed system is a system in which the buffer components can't get out. And so if you're thinking about a phosphate buffer, you can just put the phosphate buffer in saline, and all the elements of the buffer, the B, the HB plus, and the protons are all trapped inside the beaker because nobody can leave. We're going to later talk about an open system buffer. That's the CO2 bicarbonate buffer pair because the CO2 can escape or re-enter the aqueous phase. And so the buffering power of a buffer in a closed system can be described by this ugly looking equation, but the gist of it is that the buffering power is maximum when the pH of the solution is the same as the pK. And so here we're describing it as the K, but we could also put this in the form with a pK. And so when the pH equals the pK, the buffering power is maximal, and it's a bell-shaped curve. It's not the same curve that the statisticians use, but it is shaped like a bell. And what would happen if you had multiple buffers around all at the same time. The point is that their buffering powers are additive. All of these buffer reactions are going to be competing with one another for protons, but in the end, the buffering power, for example, this green curve is this green curve. But let's imagine we had 4 other buffers with lower pKs, 4 other buffers with higher pKs. Each of them is at the same concentration, and each of them has a pK that's spaced out by half a pH unit. I was just making this up, but it's an example of a complicated solution of buffers, and the total buffering power is just the algebraic sum of each of these individual buffering powers and gives you this red curve. And what's interesting is that over the physiological range, the total buffering power of all of these buffers is almost constant. Now, you might think this is highly artificial, but in our blood, there are dozens and dozens of different kinds of buffer species. The major buffer in our blood is hemoglobin, and hemoglobin has many titratable groups, and each of these has a different concentration, a different pK, but the point is that you could add them all up, and each of these little buffers is fighting with the other buffers for control of the hydrogen ions. And what we are doing here is plotting a titration curve for these non-bicarbonate buffers. If I would go backwards, what we're looking at here is the buffering power of each of these buffers. Here, we're looking at the titration curve for each of these buffers. So this is that green buffer that had a pK of 7, and what this is telling us is that the protonated form of the buffer it starts off at a high value when the pH is very acidic, and as the pH goes up, the protons come off the buffer, and eventually all of that buffer is in its deprotonated state. So the protonated version is 0. And so each of these buffers has a similar titration curve. And again, you can add all of these up. And so if you had 9 buffers, they all would add up to produce that nice looking red curve, which itself has a sigmoidal shape. And we're going to be interested in what's inside this box because that's the physiological range of buffering. So now we've described these non-bicarbonate buffers, let's talk about the CO2 bicarbonate buffer system. So the CO2 bicarbonate buffer system, of course, is described by the Henderson-Hasselbalch equation. So now let's put some real numbers into the Henderson-Hasselbalch equation. So 24 millimolar is a reasonable value for the bicarbonate concentration in arterial blood, and 1.2 millimolar is a reasonable value for the CO2 concentration obtained from the Henry's law, which tells us the relationship between the PCO2 and the dissolved CO2. So this ratio, 24 over 1.2, comes out to be an even value of 20, and if we take the logarithm to the base 10 of that 20, we get the log of 20 is the log of 10 plus the log of 2. So that arithmetic that you learned in high school actually can be valuable in medical school. So the log of A plus the log of B is the log of AB. And the log of 10 is 1. The log of the log of 2 is 0.3. If you remember those two things, you could, by addition and subtraction, calculate the pK or pH of almost any solution just by adding up pK values. So this pH is going to be 7.4, 6.1 plus 1 plus 0.3. So that's how we can use the Henderson-Hasselbalch equation to arrive at the pH, in this case, the pH of arterial blood. And so the Davenport diagram had bicarbonate on the y-axis. So we're going to want to calculate the bicarbonate concentration, and we're going to do that by starting off with this Henderson-Hasselbalch equation. And the first thing we're going to do is to subtract the pK from both sides of the equation so that you end up with pH minus pK, that's the pK, is equal to this side of the equation. And the next thing we're going to do is take the antilog of both sides of the equation. So if we take the antilog of this side of the equation, we end up with 10 to the pH minus pK. And if we take the antilog of this side of the equation, we just get rid of that ugly logarithmic term, and now we have that ratio. And finally, we can solve for bicarbonate by multiplying through by CO2. And so now you've got an equation that says that the bicarbonate concentration, and let's just flip it around the other direction, which is easier to understand. The bicarbonate concentration is equal to the CO2 times 10 to the pH minus pK. So if the CO2 concentration is 1.2 millimolar, like we just talked about, and if the pH of the arterial blood is 7.4 and the pK is 6.1, then by definition, the bicarbonate concentration we calculate is going to be 24 millimolar, just to give you an idea of how we go through this little bit of algebra. So how are pH changes then affected by bicarbonate? So let's imagine that we had that same equation we had at the bottom here, and now we're going to put it at the top of this chart. Bicarbonate is 1.2 times 10 to the 7.4 minus 6.1. And we're going to make a table in which we identify each of these terms and calculate bicarbonate. So first, let's imagine that the PCO2 is 40 millimeters of mercury. And so if the PCO2 is 40 millimeters of mercury, which gives us this 1.2 millimolar value for the CO2, then that 7.4 and now this 24 is going to be the bicarbonate concentration. You've already seen it, but I just want to show you that this is part of a pattern. And what we can do now is to take these values and plot them on this blue curve. And so this point right there is this point. The pH is 7.4, the pH is 7.4, the bicarbonate is 24, the bicarbonate is 24, the PCO2 is 40, and so we're on that blue isoplot. What would happen if instead of the pH being 7.4, let's imagine we magically change it to 7.6. It's the same equation except we've got 7.6 here, and the bicarbonate ends up being 38 right there. And so we plot that on the same graph, the 7.6 and then 38. And we can do that again. What happens if the pH is 7.2? The pH is 7.2, the bicarbonate ends up being 15, and we plot it again here. And if you do this over and over and over again, you get a bunch of red dots that represent that blue line, that blue curve. Nothing magical. This is just the description of the Henderson-Hasselbalch equation, but now plotted graphically. So what would happen if instead of the PCO2 being 40, if the PCO2 were 80, which is going to be described by this green curve? If the PCO2 were 80, then at 7.2, then the bicarbonate concentration would only be 30 millimolar, and so that's plotted here. If the we can go through this over and over again. pH 7.4, there, pH 7.6, there, and these are all just check marks here on our little table. And finally, what would happen if the PCO2, instead of being 80 or 40, what if it were only 20 millimeters of mercury? Well, the CO2 concentration would only be half as high, and that puts us in this red column. And if the pH were 7.6, then the bicarbonate concentration would be 70. That's if the pH were 7.6, then the bicarbonate concentration. This is an error. It should only be 24 millimolar. Let's go down the line. So we're going to get these three check mark bicarbonate concentrations at 7.2, 8 millimolar, right there, at 7.4, 12 millimolar, and finally at 7.6, 19 millimolar. And again, we could just fill this up with similar calculations with similar points, but I just wanted to emphasize to you that there's nothing magical about these isopleths, except to say that each isopleth describes the CO2 bicarbonate equilibrium at a different CO2 value. So how do we finally end up with the Davenport diagram? We start off with all of these isopleths that you've just seen. These describe how CO2 and bicarbonate are fighting for protons, and now you have the non-bicarbonate buffer curve, which describes how all of the other buffers are fighting for protons, and the battle is now joined, and by taking these curves and that curve and laying them on top of one another, you arrive at the mature Davenport diagram. So this red curve here is just this portion of this red curve scaled appropriately to fit on this chart. So this is the Davenport diagram, and respiratory acidosis is an example of respiratory acidosis here is point A, and so you start off, if we're at normal arterial conditions with a pH of 7.4 and 24 millimolar bicarbonate, if we now have a respiratory acidosis that raises the PCO2 to 80 millimeters of mercury, the rule is to follow this non-bicarbonate buffer curve upwards until it intersects with the isopleth that describes the new PCO2, which in this case is 80 millimeters of mercury. That's respiratory acidosis, or RAC. Respiratory alkalosis is just the opposite. So if the PCO2 were to fall to 20 millimeters of mercury, you'd end up at this point right here at point B. This complicated diagram is meant to describe to you what goes on during metabolic acidosis and metabolic alkalosis. So first thinking about metabolic acidosis, a situation in which the bicarbonate concentration goes down, or which would occur as you, for example, could add hydrochloric acid or lactic acid or keto acid, as happens in diabetic ketoacidosis. The rule here is you start off at the normal starting point, described by that red non-bicarbonate buffer line. And if you were to add 10 millimoles per liter of a strong acid like hydrochloric acid, you displace that red line downwards by the amount of acid that you added, and the new acid-base status is described by this point C right here, which is at the intersection of the PCO2 of 40 and the newly displaced CO2 bicarbonate buffer line. The metabolic alkalosis is just the opposite, that you start off at the starting point, but let's imagine you added 10 millimoles per liter of sodium hydroxide. You would move that red curve upwards. You'd redraw the curve. Now it's that black line, 10 millimoles upward displaced, and the new acid-base status is right here at point D, which represents the metabolic alkalosis produced by this addition of 10 millimoles per liter of sodium hydroxide. So the four major acid-base disturbances that you can describe in a beaker, but also in a patient, those four acid-base disturbances are: first, respiratory acidosis produced by an increase in PCO2, respiratory alkalosis produced by a decrease in CO2, and here you can see examples of clinical causes by which the respiratory acidosis can be produced, such as a decreased alveolar ventilation, or how you can get a respiratory alkalosis, for example, an increase in alveolar ventilation due to anxiety. For example, if you're up here giving a lecture and get very nervous and start hyperventilating, you'll get respiratory alkalosis. Metabolic acidosis, of course, is caused by the addition of acids other than CO2, and the metabolic alkalosis is the addition of an alkali other than bicarbonate. And again, we have examples of what can cause metabolic acidosis, such as urinary failure or ketoacidosis, for example, diabetes mellitus, and metabolic alkalosis, for example, a bicarbonate load during sodium bicarbonate therapy. So once the body is subjected to one of these four primary acid-base disturbances, it can't afford to sit around and let itself be in an uncompensated state of acidosis or alkalosis. So the body, as we outlined earlier in this lecture, has several mechanisms of detecting and responding to acid-base disorders. And so if the primary acid-base disturbance is a respiratory acidosis, the compensatory change is a metabolic alkalosis. So you take the respiratory part and you negate it to produce metabolic, and you take the acidosis part and you negate it to produce an alkalosis. So a RAC is compensated by a MELK. If you have a respiratory alkalosis, it's compensated by a metabolic acidosis. And if you have a metabolic alkalosis, it's compensated for by a respiratory acidosis. And if you have a metabolic acidosis, it's compensated for by a respiratory alkalosis. And these compensatory changes, whenever it says respiratory, it means that it's the lungs that are doing the heavy lifting by either increasing or decreasing their ventilation. And whenever you see metabolic alkalosis, it's the kidneys that are doing the heavy lifting by secreting either more hydrogen ions into the urine or fewer hydrogen ions into the urine. So this diagram is not quite as busy as it might seem if we would just focus on one panel at a time. And so we talked about the four fundamental acid-base disturbances: respiratory acidosis, respiratory alkalosis. You just follow the non-bicarbonate buffer line until you reach the right CO2 partial pressure, which might be higher or lower than the initial pH or the initial PCO2. If you have a metabolic acid-base disorder, you remain on the CO2 isopleph where you had started out, and you either go down the isopleph in the case of a metabolic acidosis or up the isopleph in the case of a metabolic alkalosis. So how do you compensate? So if you have a respiratory acidosis, you started off here with a respiratory acidosis with a metabolic alkalosis compensation. And similarly, the other four acid-base disturbances, how do you compensate for metabolic alkalosis? With a respiratory alkalosis. How do you compensate for these other two guys? The same thing. So that if you initially were at points A, C, B, and D, now you end up in a compensatory state, in a compensated state, in these different regions: the blue, the red, the purple, and the gold. Oops, sorry. And if you're perfectly compensated, the pH would come all the way back to normal. But the body never perfectly compensates. And medical students often ask me why the body doesn't perfectly compensate. Because if pH is so important, why doesn't the body, during a metabolic acidosis, take you, respiratory acidosis, why doesn't the body take you all the way back here? And if you stop and think about it, that wouldn't make good sense for organs like the heart or the brain or what have you that are very dependent upon the membrane potential of the cell. Because if the bicarbonate concentration started off at 24 millimolar, and if the PCO2 doubled, the only way to perfectly compensate it would be to double the bicarbonate concentration from 24 millimolar to 48. But how are you going to raise the bicarbonate to 48? You'd have to drop the chloride by 24. So as the bicarbonate would go up, the chloride would go down, and cells that have chloride channels or chloride-dependent transporters would not like that. So Mother Nature is met with a conflict, competing interests. Does she regulate pH, or does she watch out to make sure that the body is functioning properly? And of course, in the end, Mother Nature has figured this out through many millions of years of evolution. And so generally, the compensation for respiratory acidosis will put you here. It's never perfectly compensated, but it's compensated as much as Mother Nature feels she can get away with, considering all of the other organs in the body which are chloride sensitive. And by the way, when you see patients in the hospital, you might have a patient who has respiratory acidosis and metabolic acidosis both at the same time. So you can have a compound disturbance, and this is not so uncommon in a Shockey situation. And similarly, there are other three primary disturbances can be built upon by various combinations of metabolic and respiratory acidosis and alkalosis. So how do we control blood pH? The pH of the body is determined by the CO2 bicarbonate ratio, and it's the kidney that is controlling the bicarbonate, it's the lung that's controlling the CO2, and so very often you see people tongue-in-cheek referring to the pH of the body as being a function of the kidney versus the lung, the kidney handling the metabolic side of the ledger and the lungs handling the respiratory side of the ledger. Some of you may have heard of the term strong ion difference. Strong ion difference was invented by a physicist who retired and figured out he didn't have anything to do with his life. And so basically he re-derived all of these equations, but from a different perspective. And actually there's a lot of philosophical mistakes during the process of that derivation. And so if you should run into people talking about strong ion difference, and this tends to be intensivists who are the lung people, they've kind of gotten sucked into this strong ion difference business. It's a lot of hooey. Please focus on the Davenport diagram. Don't be focusing on the strong ion difference. Okay, so so far we've been talking about the control of the chemistry of these buffers, and I would like to tell you a little bit about the control of the bicarbonate by the kidney. And so this is a figure that's taken from the kidney acid-base chapter 39 in B&B. And if I could walk you through this, it will, in a general sense, lay out the general physiology of how the bicarbonate is handled by the kidney. So every day we have a diet which has a net acid load of about 20 millimoles of hydrogen per day, and that's taken up by the gut. And also in the feces, we lose about another 10 millimoles per day of alkali in the feces. And so between this 10 coming in and an extra 10 of hydroxyl going out, we've got a net uptake of about 30 millimoles per day of acid when we look at the GI tract. And On top of this 30 millimoles per day, there's another 40, so this represents an acid load that ends up in the extracellular fluid. And on top of this acid load, due to the diet and the loss in the feces, we also have various tissues in the body performing metabolism, and the metabolism of various amino acids and so on ends up producing about 40 millimoles per day of non-volatile acids. And if you add up this 30 and this 40, that adds up to 70. And so every day, the kidney must release into the urine at least 30 plus 40 or 70 millimoles per day of acid. Otherwise, you'd continuously build up acid in your body and die of metabolic acidosis. And so, but on top of all of this, every day, the kidneys filter about 1 pound or roughly a half a kilogram of sodium bicarbonate, and so every day the kidneys lose into the primary reabsorb fluid from Bowman's capsule about 4,000 or so millimoles per day of bicarbonate, and they also have to reabsorb that bicarbonate. So they filter 4,320, but they have to reabsorb 4,320. And so this filtered load of bicarbonate is the price that the kidney pays for control. But the first thing the kidney must do is to reabsorb all of that bicarbonate. So on the one hand, most of the work of the kidney is just to reabsorb the bicarbonate that is filtered. But if you reabsorbed every last bicarbonate ion, you'd still die of metabolic acidosis because you've got to create 70 millimoles per day of new bicarbonate. And this is produced by secreting 70 extra millimoles per day of protons, and I'll show you how that happens. By the way, the lungs get rid of the CO2, so metabolism produces 40 millimoles per day of hydrogen ions, but metabolism also produces 15,000 millimoles per day of CO2 that goes into the lung, and we just exhale it and don't have to do any more worrying about the CO2. So normally, bicarbonate reabsorption merely cancels bicarbonate filtration in the glomeruli, but it's the acute and chronic adjustments of these rates that make compensation possible. So it's possible for the kidney to adjust this arrow, to adjust this arrow, and thereby adjust these two arrows. So now I'd like to tell you a little bit about hydrogen secretion along the nephron. So this is an artistic view of the nephron, and what happens is that every day the bicarbonate in the arteriolar fluid is filtered into Bowman's space, and this, as I mentioned, amounts to, if I were talking to Americans, 1 pound of baking soda, 400 and some odd grams of baking soda, and this bicarbonate must all be reabsorbed, and about 80% of it is reabsorbed in the proximal tubule, about 10% of it is reabsorbed in the thick ascending limb, and another 10% is reabsorbed in the distal nephron, so that normally we have almost no bicarbonate remaining in the urine. This just takes care of the bicarbonate that was filtered. So how does that occur, that bicarbonate reabsorption? So the bicarbonate that was produced by glomerular filtration, this is now in the tubule lumen of the proximal tubule. We have, actually there are 3 transporters, and the classical view is that there are only 2 that both secrete hydrogen ions. I'll tell you about the most recent discovery in just a minute. But these 2 transporters, the sodium hydrogen exchanger 3 and a vacuolar type ATPase, both secrete hydrogen ions as a result of an energetic consumption of energy, and these hydrogen ions end up in the lumen. Here the energy comes from the sodium electrochemical gradient. Here the energy comes from the splitting of ATP. In any event, the hydrogen ions that are pumped out into the lumen react with bicarbonate ions to produce CO2 and water, and this reaction is catalyzed by carbonic anhydrase 4. It's an enzyme like carbonic anhydrase 2, which is a soluble enzyme we'll see is present in the cytosol. This is GPI linked to the outer leaflet of the membrane, and this enzyme allows this reaction to proceed very rapidly. And now the CO2 will enter the cell along with the water, and most of the CO2 and most of the water are moving through aquaporin 1, which are water channels, but aquaporin 1 can perform a little bit of magic. In addition to allowing CO2 to go through, allowing water to go through, it also allows CO2 to go through. And just as an aside, the aquaporins are tetramers. It's like having 4 American donuts on a plate, and each donut has a donut hole, and each donut hole is how the water gets through, and the hole in the center of the donut is hydrophobic, and that's how most of the CO2 gets through. And so that's what our laboratory discovered. And so the CO2 and water, once inside the cell, will recombine, catalyzed by carbonic anhydrase 2 to form hydrogen ions and bicarbonate. The bicarbonate then exits the cell together with sodium on NBCE1A. We discovered and cloned the cDNA that encodes NBCE1A. So for each hydrogen ion secreted into the lumen, 1 bicarbonate disappears from the lumen and 1 bicarbonate appears in the blood. But the bicarbonate doesn't just go from here to here to here. At least in this classical view, it's hydrogen that are secreted there, CO2 that crosses the membrane, and bicarbonate which exits there. So this is bicarbonate reabsorption. So this is responsible for the reabsorption of 4,000 some odd millimoles per day. This is the heavy lifting, but all of this does is get you back to 0. If you're going to neutralize the acid that's produced as a result of metabolism, you have to form new bicarbonate, and this is how you can form new bicarbonate. I'm sorry, these chairs, I may make matters so that you could read the bottom line. So many buffers can be titrated in the lumen, major ones being phosphate, creatinine, and urate. And so these are filtered in the glomerulus, and let's just take an example, dibasic phosphate. and it will react with these protons to form monobasic phosphate H2PO4, that's one negative charge. And for each hydrogen ion secreted into the lumen, one bicarbonate appears in the blood. And so this is an example of the creation of new bicarbonate. So the bicarbonate that appears in the blood never was in the lumen. That bicarbonate was generated from CO2 that entered from the blood, and then that CO2 is converted to bicarbonate. Another example of the creation of new bicarbonate is that the kidney is able to metabolize glutamine and glutamate to form ammonia, which moves into the lumen. So this ammonia, which ends up in the lumen, also is titrated by hydrogen ions, and to produce now the conjugate weak acid ammonium. And for each hydrogen ion that's secreted, one bicarbonate appears in the blood. So that bicarbonate that appears in the blood never was in the lumen. It's created from the deficit created as these hydrogen ions move into the lumen that allows from CO2 entering from the blood, that allows the formation of a new bicarbonate that ends up in the blood. And it's this new bicarbonate which is titrating off metabolic acids that are created as a result of cellular metabolism throughout the body. Another example of new bicarbonate. Now, just in case I haven't been complicated enough, I'll show you a brand new slide that this is a former postdoc of mine in China by the name of Li-Ming Chen, and we were part of this paper by Guo et al. That appeared last year. And the reason why this was an important paper is because it was the first example showing that in the apical membrane, in addition to the sodium hydrogen exchanger 3 and the proton pump, there's yet another transporter here, the NBC-N2. Let me take off the orange egg that was overriding it. This sodium bicarbonate cotransporter electroneutral number 2 directly takes up bicarbonate along with sodium. And so this is an example of the direct reclamation of baking soda by a transporter in the apical membrane of the proximal tubule. So this is just another example of the transporters. So throughout the nephron, pretty much the same process occurs, although there are different players doing the work. So in the proximal tubule, we've already talked about NHE3 and the proton pump. Later in the proximal tubule, there are different transporters in the basolateral membrane, so that in addition to NBC, you'll also see a chloride bicarbonate exchanger. In the thick ascending limb, again, you'll see sodium hydrogen exchange and proton pumps, but now a chloride bicarbonate exchanger known as AE2. And then in alpha intercalated cells in the distal nephron, you'll also see now another bicarbonate transporter at the basolateral membrane, AE1. But basically, you've got acid secretors on the apical side, bicarbonate secretors on the basolateral side, and in general, that's how the job is done in the kidney. One other thing that's going on is understanding the molecular mechanism of the secretion of the ammonium. This is a very complicated slide, but it does illustrate for you. You can go back to the textbook and see the biochemistry behind the uptake of glutamine and how when glutamine is taken up either from the blood or from the lumen, salvaging glutamine that's filtered, how that glutamine is metabolized in the mitochondrion and in the process generating ammonia, which leaks out into the lumen and then is titrated by hydrogen ions. And in the end, this ammonium ends up in the urine. And so, if we're now thinking about how all of these processes are regulated, again, this is a very busy slide, but I just like to briefly point this. You've seen all of this stuff already, and I'd just like to point out that the major regulator that's present at least in the proximal tubule, although we know it's also present in distal segments of the nephron, is a protein called receptor protein tyrosine phosphatase, RPTP gamma. And this little area of the molecule is a tyrosine phosphatase, which will knock phosphate groups off phosphotyrosines on ERB1 or ERB2 or other proteins as well. And what's really interesting about this molecule is its extracellular binding site looks like carbonic anhydrase, except it's enzymatically inactive. So Mother Nature has mutated several amino acid residues of a bona fide carbonic anhydrase and made it so this is no longer an enzyme but a binding protein that we call the carbonic anhydrase-like domain as a sensor. And when bicarbonate is bound, it appears that this is a dimer and becomes enzymatically inactive here. So this phosphatase no longer works, whereas when the CO2 concentration goes up, it displaces bicarbonate, and now these RPTP gamma molecules monomerize and are able to do their phosphorylation job. So in the proximal tubule, which is designed to help regulate the pH of the blood, the proximal tubule doesn't know what the pH is. It is sniffing the CO2 and sniffing the bicarbonate concentrations in the blood. And so it somehow magically measures the CO2 bicarbonate ratio and transmits that signal by dephosphorylating tyrosine groups. This diagram illustrates something about the chronic regulation of renal hydrogen secretion. This regulation happens within minutes. And then in a more global sense, if the body undergoes metabolic or respiratory acidosis, which also decreases the intracellular pH throughout the body, a number of different pathways are triggered. For example, the tyrosine kinase and I should say phosphatase pathways. And in the longer run, there's upregulation of various transporters or enzymes that are necessary either for producing the ammonia that ends in the urine and this is also part of ammoniogenesis, and these are the transporters that we talked about already, which are important for either the reclamation of filtered bicarbonate or the generation of new bicarbonate. So we've already ticked off several of these major bullets, and now I'd like to tell you a little bit about the control of CO2 by the lungs. And just to remind all of us, so this is a diagram taken from this figure 31 in the textbook, and so this is meant to represent alveoli, conducting airways, and so this describes how we get rid of CO2. So at the end of an interbreath period, CO2 has built up in our alveoli, and now what we've just finished exhaling, and now what we're going to do is to inhale some fresh air, and this fresh air has no CO2 in it, and so after that CO2 is diluted, there's the CO2 concentration here in the alveolar space is less than it was before, and now we're going to exhale the CO2-rich air, and with every breath, we're exhaling about 18 milliliters of pure CO2 gas. So when we exhale a lot of things. We exhale oxygen that we haven't used up, we exhale nitrogen, we exhale some water vapor, but we also exhale in a 500 milliliter tidal volume, we exhale 18 milliliters of pure CO2 gas. So that's how we get rid of the CO2 that our body produces metabolically. And so the CO2 concentration in the alveolar air, let's say right here, is proportional to the volume of CO2 that you exhale, in this case 18 milliliters, divided by the volume of exhaled alveolar air. So if you just finished exhaling 350 milliliters of alveolar air, don't forget that the first 150 milliliters out of your body was from your conducting airways that don't have any CO2 in them. So if we just looked at the exhaled alveolar air, 350 milliliters, 18 milliliters of CO2, and so we could calculate the CO2 concentration. And that concentration is the volume of CO2 exhaled divided by the volume of alveolar air that's exhaled. And that's going to be equal to the CO2 concentration in the alveolus, but it's also proportional to the CO2 partial pressure in the alveolus. And then we end up with this equation in which the proportionality constant is now made plain at 0.863, and so the alveolar partial pressure of CO2 is inversely proportional to the amount of alveolar air that we exhaled and proportional to the concentration of CO2 and that alveolar air, and this is true breath by breath. But it also can be, this whole rule can be applied per minute. So every minute, how much CO2 do we exhale? Well, we put that little dot here. And so rather than thinking about 18 milliliters of CO2 in one breath, now we're thinking about how many mils of CO2 in 1 minute, and that would be about 250 mils of metabolically generated CO2, and then the alveolar ventilation would be about 4,000 milliliters of air. And so we can take that equation that we just saw, that the alveolar partial pressure of CO2 is inversely proportional to the alveolar ventilation, and now we're going to generate this curve in blue. And what this curve is telling us is that with a normal alveolar ventilation, so normally we're ventilating 4,200 mils of alveolar air leaving our body every minute, and so what's happening is we're exhaling about, in this example, 200 milliliters of CO2 gas is being exhaled along with 4,200 milliliters of alveolar air. And so we divide this by this. If this is in liters and that's in milliliters, then it's 0.863. And you end up with a PCO2 of 40 millimeters of mercury. So the fundamental principle to understand is that every molecule of CO2 that you produce during metabolism, every single molecule in the steady state must be exhaled. If you don't exhale all of the CO2 that's produced by metabolism, the CO2 will start building up in your body, and eventually you'll end up being a block of dry ice. That's meant to be funny. So if you if you retain all of the CO2 that you produce metabolically, the CO2 level will go up and up and up, and eventually they'll carry you away as a block of dry ice. So you have to get rid of the CO2 that you produce metabolically. So let's imagine that you are hyperventilating like this. A new steady state will eventually be achieved, but I'm now ventilating twice as much as I was before, but I'm still only producing 200 milliliters of CO2 gas every minute, but I'm now ventilating my alveoli with 8.4 liters per minute, and so the concentration of CO2 in the alveolar air must be half, because I'm ventilating with twice as much air, but I'm still only getting rid of the same amount of CO2, so the CO2 concentration falls in half, and the PCO2 falls in half. What would happen if you were in respiratory failure and were only exhaling 2,100 milliliters of air every minute, but still were producing this much metabolically? Now the PCO2 concentration doubles. It has to double, because your body has to get rid of that CO2, and the only way to get rid of it is in the alveolar air. So you tell me how much alveolar air you're willing to invest in this process, and I'll tell you what the PCO2 is, because in the end, we're getting rid of 200 milliliters of CO2 every time, and you generate this right rectangular hyperbola that looks like this. And it's a very important right rectangular hyperbola, because physicians, by looking at the alveolar partial pressure of CO2, will guesstimate what the alveolar ventilation is. And so if a patient comes into the ER and has a PCO2 of 80 that just happened a couple of hours ago, you would presume that their alveolar ventilation has fallen in half. Okay. So because CO2 is transported into the alveolar blood by a diffusion-limited process, the arterial and alveolar PCO2s are nearly the same. And so when we talk about alveolar CO2 partial pressure, this is also the arterial CO2 partial pressure. And the body controls the CO2 by controlling ventilation. So as the CO2 concentration goes up, 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 your body will try to raise the ventilation to make the CO2 come down, down, down. So how do we control ventilation? By peripheral chemoreceptors. This is an overview about how the body controls respiration in general. let's start right here with a central pattern generator in the medulla. That central pattern generator will send neurons down to the spinal cord and eventually to the muscles of respiration that make the chest wall move, and that produces ventilation. So when everything is going well, the CO2 is low, the oxygen is high, but what happens when things don't go well? What happens if the PCO2 goes up, or the oxygen goes down, or the pH of the arterial blood goes down? These are changes that are detected by peripheral chemoreceptors, which then send information by either cranial nerve 9 or 10 to a signal sensory integration center near the NTA, the nucleus tractus solitarius, NTS, and that will then trigger the central pattern generator to increase the ventilation to counteract these unfortunate changes. In addition, the CO2 can cross the blood-brain barrier and be sensed by central chemoreceptors. See it in a second. So this is an example of a single gloma cell from the peripheral chemoreceptor, the carotid body, and it shows how anoxia, a low level of oxygen in the extracellular fluid, will cause the firing rate of the cells, these gloma cells, to go markedly up, and that is then transmitted along cranial nerves numbered, depending on whether you're an aortic body or carotid body, cranial nerves numbers 9 and 10. And so now if you look at an integrated response here, what you see that is as the arterial PO2, which is normally right around here, as the arterial PO2 goes down, 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 the impulses per second from these gloma cells will go up, up, up. So the body is sensing the hypoxia, and the greater the level of hypoxia, the greater the firing rate. But it's interesting that these gloma cells are able to do some integration on their own. So if you have respiratory acidosis, the firing rate is higher to begin with, and it goes up even more steeply. If you have respiratory alkalosis, the firing rate is lower than it was here, and it goes up much more slowly. So the combination of hypoxia and respiratory acidosis feed against one another to produce an elevated response. And so you can see here at a given PO2, let's say 60 or so millimeters of mercury, as the pH goes from a high value to a low value, the firing rate goes up, up, up. And also the steepness of these curves go up, up, up as you go up the curve. If we keep the CO2, if we vary the CO2 but keep the pH constant, so this is an experiment done always at pH 725. How do you change the CO2 and yet keep the pH constant? And the answer, of course, is you make compensatory changes in the bicarbonate concentration. So here, the bicarbonate concentration may have been decreased by 25% or so. So you have a change in this bicarbonate CO2 ratio to drop the pH to 725, but you're adjusting the bicarbonate concentration at the same time you're adjusting the CO2, so the pH is always 725. Here, if the pH is 745, slightly alkaline, that same curve is downwardly depressed, so that acidity per se, as you go from 745 to 725, that even at a constant CO2, that makes you breathe faster as a result of the gloma cell. But in addition, the gloma cell is able to sense the CO2 level. So the gloma cell is able to sense CO2 per se, is able to sense pH per se, and is able to sense oxygen per se. And finally, the central chemoreceptor. So the central chemoreceptors are located mainly in the brainstem, mainly in the medulla, but to some extent in the pons. And I would just like to point out to you two of the areas that are important. The ventrolateral medulla, this is a cross-section like slicing through a sausage, and this is the ventrolateral medulla, this is the medullary raphe, and they have a rather interesting set of neurons. And in this medullary raphe region, there's some neurons that are inhibited by acidosis. So if this is and other neurons that are stimulated by acidosis. So this is an example of a control situation for a particular neuron, and you can see the normal firing rate when the CO2 is 5%, and then here the CO2 value is 9%, and now you see the rate of firing more than doubling. And so this is a result of a neuron in the medullary raphe sensing the acidosis, a respiratory acidosis produced by an elevated CO2 level. And so you can see this in a living animal if you're looking at ventilation, and then in a living animal you suddenly give it CO2 to breathe. So here the air that's inspired has no CO2 in it. There's also no CO2 there, but for a short period of time, we have the animal breathing air with CO2 in it, and that causes the ventilation to rise. Actually, it rises rather slowly. The CO2 level in the brain hits its final value almost instantly, but it takes a long time for whatever signal transduction system is working to eventually raise the ventilatory rate of the animal to compensate for the high level of CO2. So this is a ventilatory response to a ventilatory increase in the CO2. How does this occur? This is the central chemosensitive neuron. It's on the opposite side of the blood-brain barrier from the blood. And so as the CO2 level is going up in the blood, it acidifies that area around the neuron. And as a result, what you see is as the cerebral spinal fluid, in the case of this experiment, gets more and more and more acid, the alveolar ventilation goes up, up, up. And this is more effective if this acidification is produced as a result of a respiratory acid-base disturbance. And so if the pH of the arterial blood goes down, 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 the pH of the CSF will go down more steeply and more rapidly if it's a respiratory acid-base disturbance. In other words, if the pH goes up and down because of CO2 changes, much more steeply than if the insult is a metabolic acid-base disturbance. So if we lower the bicarbonate, it's not as effective as raising the CO2 in terms of, geez, World War II mystery solved after 74 years. Well, we'll have to go investigate. We'll have to read that on the internet when this is over. Maybe it's... Okay, so the grand outline then, we've talked about we gave you a brief introduction. We've talked about the chemistry of buffers, the control of bicarbonate by the kidney, the control of CO2 by the lungs, and we now give you the grand summary, just briefly showing you the picture that you already saw. That, of course, the lungs are right at the center of all of this. The lungs are what controls the ability to excrete the CO2 that you produced as a result of metabolism. So the mitochondria generate CO2, and all of that CO2 must be ventilated into the external air. And so that's one part of the equation for controlling the PCO2. And the other part of the equation is the kidney, which is able to sense CO2 and bicarbonate by this RPTP gamma, and thereby control how much hydrogen ion is being secreted into the urine. And so these two organs, the brain and the kidney, together are controlling the CO2 and the bicarbonate, and they work in cahoots to keep the pH of the blood as constant as physiologically possible. And the main takeaway message then is that the pH of the blood is a constant plus some function of the kidney and the lung, the kidney controlling the bicarbonate metabolic acid-base balance, and the lung controlling the respiratory acid-base balance. So in closing, I'd like to thank you for the invitation to be in La Plata this afternoon. I'd like to let you know that if anybody wants to get in touch with me, this is how you can do it, by sending me an email at walter.bourne@case.edu. And if there are graduate students in the audience who are looking for a postdoctoral fellowship in the general areas of acid-base physiology, now mainly on the cellular level, or also on gas channels, I'd be happy to hear from you at some point in the future. So again, thank you very much for the invitation. I'll be happy to answer questions. Thank you.
You're going to wrap your book or textbook now, and probably you can sign it for someone.
Sure.
I'm going to pick it. Bueno, por supuesto agradecerle al Dr. Boron por su excelente conferencia, agradecerles a ustedes, y antes de que se vayan, tienen los numeritos, vamos a sortear uno de los libros del Dr. Boron para que él se los pueda firmar a quien se lo haya ganado. Dice que es la primera vez que ve este libro, porque es la versión en español, entonces dice, no sorprenda. Nosotros le preguntamos cuánto tiempo estuvo trabajando para hacer el libro, la primera edición. So we asked you about how many years have you been working with the book?
Geez, how many years have I been working on it? We started in 1989, and it took us 5 or 6, so it took us from 1989.
Yes.
From 1989 to about 1995, we were collecting chapters and getting depressed because there was just so much that needed to be done. And we began to organize things, and we realized that as different authors, because this book is co-authored by about 20 different people, and each of these people write with a different depth, a depth of a different depth of just how detailed do you explain the material. They write with different writing styles and different lengths, and so it was a real mess. And so we then, from 1995 to about 2001, Emil Bullpop, the co-author, and this is a man, Emil Bullpop, we worked every day from 5 p.m. So I have a laboratory, and every day I would leave the laboratory at 5 p.m. and he and I would work from 5 p.m. till 7 p.m. Monday, Tuesday, Wednesday, Thursday, Friday, and on either Saturday or Sunday we would come in for about 5 hours. And so we worked 6 days a week. You can add that up, 15 or 16 hours a week for 7 years. And that's what it took to go through the book. And so it's a book written by 20 authors, but designed to feel like it's written by one author, and linking the words to the text, the words in the text, linking them to the figures, and working with the art studio to get the figures right. So this was 7 years of intensive work after about 6 years of laziness, but altogether about 13 years to produce the first edition. And now we're preparing for the 4th edition, and we never stop working. It's just, you publish one version and then you start working on the next edition. So, but it's a work of love, and I never thought we'd get the 1st edition out, but now that the 3rd edition is out, I'm sure we'll get the 4th edition out. I hope I'm still living.
Okay. Bueno, a ver, alguno de los chicos que cursó el año pasado con nosotros, para que alguno que esté más o menos cerquita, que baje para así hacer el sorteo, ¿sí? Tienen que... Sistema más moderno de sorteo. A ver, ¿quién baja? ¿Qué? De este año, sí, de los chicos que cursaron este año, claro, de los chicos que cursaron este año.
So you're telling them about sign up?
Yes, they can. It's just, we have to do the... ok, nadie quiere bajar. Fiorella, a ver que estás ahí cerquita, dale. Sí, dale. I got it. Porque si no van a decir que yo lo arreglé. You can hold it.
I was just going to say that if people have a copy of the book that would like me to sign, I'd be happy to do that. Just make sure it's your book. It's no fair stealing one from the library or whatever.
Bueno, hacemos el sorteo, ¿sí?
32.
Oh, you're right.
32, ¿sí? Muy bien.
So, oh, you win.
She won.
Oh, congratulations.
You can write down her name. So
Okay,
you can sign
sure.
it.
Why don't you want to do that? Yeah, your name.
Sí, ahí. Ponete ella si te sacan una foto. Ay, bien.
You want to write your name? So,
Yeah, I got it.
someone. You'll go out? It's an R. R-A-R-O. R-A-R-O. And today is 12th of November. There you go. Well, congratulations on getting into it. Yeah, there you go.
Okay, thank you so much.
Well, congratulations.
Bueno, muchas gracias a todos y a todos ustedes los esperamos el 22.